Hello, and welcome to this talk on designing AI-based medical imaging methods for generalizability and reproducibility. I've given this talk a couple times within the past 6 months. Got some great interest and also feedback, so I'm putting this out there for hopefully more of you all to see. Please feel free to reach out, leave comments here, and every time I've gotten feedback, questions, it's been really helpful and updated some of the content that is in here. So I want to start off thinking about, well, this talk is going to be some general thoughts, and I'm not an expert in all of these areas, but try to give you some flavor of what I see out in the medical imaging field and AI and where there's opportunities. But we have to first start off with some definitions. What do we mean by either reproducibility or generalizability? Reproducibility, more specifically, is referring to the method working the same every time, and that can be slightly different interpretations, but maybe it's for the same individual, or maybe it's for the exact same data set. But that's what we want in terms of reproducibility. And then generalizability is a little different. It's more that we want the method to work across some broader distribution of what we expect for the input data. So this could be maybe broader patient populations, could be different institutions or different vendors of medical imaging devices, even some tolerance to different image acquisition or reconstruction parameters as well. And so a couple of topics I'll go through here. Data is maybe obviously very important, but also thinking about some more engineering-based techniques we can apply, such as physics-based machine learning, Bayesian methods, some ways to predict generalization, and federated learning. At this point, I think the challenges of reproducibility and generalization are very well known and very well documented in the context of AI and its application to medicine in general, but specifically medical imaging. A few articles discussing that, and even this memo on the side here from the United States Food and Drug Administration, where they're having strict requirements on testing of the generalization of AI methods that are being used for medical imaging. And why is this such a challenge for medical imaging? I think there's a sort of general issue that deep learning models and AI methods can be relatively brittle, especially depending on the training data, the amount of training data that is used. So if we have data that falls outside of our original training data distribution, that's often problematic. And then in medical imaging, we're often dealing with a situation where our data sets are smaller than those where there's been the greatest success from computer vision, for example, of large amount of images. You can scrape tons of images and data from the web. We don't have that luxury, especially because we have to respect patient privacy. That makes image sharing and other data sharing more difficult. And often our annotations may be very expensive to come by, depending on the level of expertise required to obtain those. And then a couple things that I mentioned before, but we have changes to devices that can cause variations. We have, and as well as the vendors' reconstruction algorithms in the imaging protocols. And finally, the stakes are high, right? We should have a very high standard and a very low error tolerance when applying AI to medical applications where we're making important health decisions for people. So just a few thoughts here on data, maybe the obvious part of what's needed for reproducible AI. And if you look out there in the area of chest x-ray, it really has the most mature algorithms because there's a lot of data. And I would also add that chest x-ray, there's relatively few things that are varied in the imaging, how the imaging is done. It's pretty straightforward procedure. You're going to get relatively consistent appearance and contrast within the images. On the other end of the spectrum, the modality I'll talk about a lot here is MRI. And not only is it less common, but we have this wide range of MRI scan protocols and sequences that amongst institutions, and I can speak even at my own institutions, their variability in the contrast because of the sequence parameters or the vendors that are used for MRI scanning. And I think usually a good thing, there's continuous updates to the acquisition methods and the hardware, but this just adds to the type of data our methods must be able to work on. I want to highlight. So there's a few clear things we can do in terms of data to lead to better solutions. Again, obvious, more data. Maybe also kind of obvious, especially in the context of generalization, is we can try to include data from a broader range of institutions, or that very concept very generally. And I think something very much worth considering as these methods get deployed is forms of active learning. So this means, your model's been trained on some previous set of data, but you're doing periodic updates based on new data, new annotations coming in. And then another area that can actually go a long way too is that is kind of some parallel efforts within multiple medical imaging communities is, well, how can we just from the get-go have a better standardization and harmonization of our images? So you just are going to reduce that the distribution of the data. So we're going to reduce some of that variability due to how maybe the images are acquired or processed from the beginning before they even go into our AI methods. And in terms of having more data, one really fantastic recent effort was the RadImageNet project. And this is where they gathered over a million total images coming from over 100,000 individual exams across CT, ultrasound, and MRI, with some annotations in place there, where the first application they're looking at this is for use in transfer learning, which you see a lot of research right now being done from training done on ImageNet, and then transfer learning to go into the medical imaging domain. Here you start in the medical imaging domain and expect to have some nice gains there. And I see these kinds of efforts, again, just providing more data can really go a long way for the improvement of generalization of medical imaging algorithms. Okay, so moving on from data, the first methodological approach I want to talk about are physics-based AI methods. And here the idea is, well, we have really good physical models for MRI and other imaging systems, so let's incorporate these explicitly into the AI methods. And this prior information may really help guide our reconstruction and improve reproducibility. And MRI really has been a rapid adopter of these types of methods. Coincidentally, last month, this special issue came out for IEEE Signal Processing magazine that I encourage you to check out if you want some more information in this area. And we can start off with a baseline model here, a kind of UNet, and this is a not physics-based model. I'm going to preface this that has image to image, kind of what you might naively could expect for the image MRI reconstruction problem. And it works reasonably well, but it has some shortcomings methodologically, and then it's that are listed here. But really, it's important it's not a physics-based method, and maybe because of this, or but we also have the other issues of potentially how the algorithm was developed and training data. You can lead it to examples like this, where the left is the reference with some lesions here that when you ran through a deep learning reconstruction can, in fact, smooth those out if those were not seen in the training data, or maybe if you don't have the physics-based constraints that I'll show next. So the physics-based methods that are used in MRI reconstruction are really built around algorithm unrolling. Unrolling these optimization algorithms like gradient descent, ADMMM, that in fact, if you unroll, do look like deep networks. But these algorithms have a data consistency term, ensuring that in the case of MRI, the k-space Fourier space raw data matches with the Fourier transform of the reconstructed image as a way to basically enforce the physics. So here's an example of a gradient descent inspired unrolled network where here's what the update looks like for gradient descent, and you have a block that's enforcing data consistency based on the acquired data, this raw data with the red lines on it here, the coil sensitivity, which is another unique part of the MRI reconstruction problem, but then uses trains a regularizer. It's a CNN-based regularizer to learn things like the typical patterns, features you might expect in medical images, and also how to remove artifacts. And so stacking these together, we maintain this data consistency at each step or each stage here of the reconstruction process. And this ensures some physics-based constraints can be kept in the model. And then it turns out these unrolled networks are also more training data network size efficient than UNets. And here's another example of really some of the state-of-the-art in the MRI field. This is an example called MODL. That's ADMM inspired, but again using a CNN-based denoiser. And some refinement of these algorithms, but these have become widely adopted in the MRI community. And as these results show, that our optimization methods, the middle column here of CG sense and total generalized variation, that really the unrolled networks are outperforming these, delivering on what we hope is the promise of AI methods, and doing it with this physics constraint to hopefully improve reproducibility. There are some ongoing challenges where there's some interesting active research. One is that how do we deal with the complex valued raw data and image data in MRI? You still need to be concerned about a domain shift and figure out, well, how much of a problem could that be, even if we have the physics constraints? And not only sort of domain shift, the example here is domain between neuro and knee, but also other types of domain shifts that could come from a number of things in MRI, such as the coils, the acquisition, and the undersampling schemes. Okay, sort of moving on to the next area that I want to discuss, which is how can we assess the confidence of our AI methods. And this is where I'll talk about Bayesian methods and other approaches for trying to predict reproducibility or generalization. And here we want to come up with some other output along with the AI method that gives us some confidence in the answer. If this is an image-based task, we have an image output task, we want to have that confidence on a voxel-wise level. If it's a classification type task, then for the classified answer, it is important to have some metric there and predict cases where we don't know the answer, what the generalization performance of the model might be. I should note for some of these things, when conventional approaches, a reconstruction and a radiologist looking at it, they're very familiar with how noise, other artifacts kind of propagate and affect the images, and they can sort these out by sort of learning themselves of, well, what's artifact, what's real. And I think in AI methods, it's sort of to be determined as to how much can the human observers, either of the images or of the results, understand what might be artifact or incorrect answers versus being kind of tricked, right? And whether can we bring on some of these other metrics to address this? So I'll talk about a couple approaches that use Bayesian machine learning. Now, two examples. One example here is for the problem of creating synthetic CT images from MRI images, kind of illustrated in the example at the bottom, where we might take several MRI images as input and try to create a CT as an output. This has applications in PET MRI, as I'll show later, but also MR-guided focused ultrasound and in radiotherapy planning. And the reason why we looked into this specific area and why we needed something with more confidence is that actually the data in this case is pretty messy. Sometimes there's a mismatch between the CT and MRI data. Could be because, for example, changes in anatomy like the bowel and the air. And then that MRI data in itself actually has a lot of problems with artifacts from motion and what the example that I'll show, implants. So how can we figure out what is kind of going on in those cases? And these are either edge cases or they're cases that are just hard to solve because of the data quality itself is poor. So the solution that we tried for this case was something called a Monte-Carlo Dropout Bayesian CNN. And the approach to this is relatively simple. There's two steps. So one is during training, you're going to apply a dropout layer to all the convolution operations. But the important thing about that dropout is you're going to do it in some stochastic, so some random fashion. And then the next part of it is you're not just going to train one model with this stochastic dropout. You're going to repeat training multiple times, get n copies of the model. And since you do stochastic dropout, there's going to be some variations in the parameters across the models. And then you can run inference on the ensemble of models and get an ensemble of predicted outputs. And from these predicted outputs, compute a mean, so your kind of average answer, what you might expect if you had a single model, but also critically now we get a variance image here. And so this potentially is what you can look at to get some measure of confidence in the result from this CNN. So here's an example trained on hip or pelvis imaging data of MRI and CT, trained on patients without implants, and then tried to extrapolate on unobserved data and actually an area where you have poor quality training data because of these large black holes, which are due to hip implants in these three patients that we tested on. Okay, so if we take our model, create this pseudo or synthetic CT estimate, and see where there's no implant, okay, they look pretty reasonable. And then this black hole in the MRI of the hip implant starts to appear as a black hole on the pseudo CT. And this is, in some applications, this is going to be a massive problem because, in fact, this is the opposite. The implant should have very, very high attenuation, photon attenuation, not a very low photon attenuation. But what we see with this Bayesian CNN approach is the standard deviation map now clearly highlights that this implant region is out of distribution. The model really doesn't know what to do with the signal in this area. So it really flags this as, okay, this is problematic. We should probably not trust this synthetic CT in this region. You can also see it highlights the bone, which is where these methods typically struggle, as well as some patches up here on the top of the image in the second column that correspond to where there's air in the bowels, which there's mismatches in the training data for that, so the algorithm struggles with what to do there. So in this case, we could actually, beyond an interpretation, we could actually use this information in the PET reconstruction in a PET MRI scenario by running a maximum likelihood reconstruction of activity and attenuation, MLAA, where we can actually enforce an MR prior penalty based on the variance image here. So using as much side information of the synthetic CT as we can from MRI, but knowing where we are not confident in the synthetic CT and then putting that into this regularized reconstruction. And when we do that, the PET data now is also used to update the attenuation map, where we now see this bright region corresponding to high metal attenuation, and we see some pretty nice reconstruction of the PET image that I'm quite happy with. And a similar technique to this has been applied to uncertainty estimation for MRI reconstruction. So the idea is a bit similar. We're going to create multiple copies of our reconstruction model, but in this case, draw some model parameters from a normal distribution to create this variation across the models. And then again, run inference on all the models, compute the mean and standard deviation. And we can look at uncertainty in the bottom left, both here in k-space, as well as in image space, and see the areas, okay, where the reconstruction is having more challenges or less confident about the answer, which we see the high resolution features. Makes sense, we're throwing out high resolution k-space data, and then some of the high intensity structures as well. Now shifting gears a little bit, there's a couple of other ways we could potentially look at trying to create a metric or some idea of, well, how either reproducible or generalizable is a model. This was an interesting approach I came across called drift detection. And the idea here was, you got a model, you're running it at your institution, and you want to see, well, you're putting new data into it. Is it still applicable for that data? And so this work, they created a drift metric called MMC. Includes part based on the images, which I'll talk about in a second, but metadata and also output of the model, so a sort of a combined metric here. And part of I think the innovation here is this specialized encoder-decoder that was trained to create some feature encoding space where we might be able to identify out of distribution data, but in a lower dimension space, or capturing features of the image as opposed to how do we determine this image is so-called out of distribution. And so this encoder decoder and having a feature space there to look at might be the way to do that. And there's a very compelling example that they tried using a model trained for chest X-ray detection of pneumonia. And the design here that was interesting was it was trained on adults, but at some time here, time A, they started running it on pediatric cases as well. And this MMC metric, so it's a combination of the metadata, these feature space data, as well as the model outputs. This metric dropped drastically, suggesting there's some drift in the incoming data, and the model is probably not performing well on this data. And so I could see a number of applications for this, especially for maybe you have an imaging system that's evolving, like MRI or MRI sequences. It could happen with other modalities as well. It's kind of detect whether a model's still good. Another approach, similarly looking at generalization from the perspective of analyzing interior feature space, but in the actual model itself in this case. This case trying to look at the assuming that a good model, a generalizable model, should begin to have some kind of clustering or reduced some pattern to the data in the interior feature space, prior to the prediction, that this would be a good way to assess generalization of the model and potentially how well a new unseen data set might perform. So on the right here, these are pulled to actually a model that's poorly performing on a test set, in one representation of the interior feature space, it doesn't show this nice separation that the good model would show here. So another approach, can we look at the interior feature space of these models and learn something about generalization performance? And Dr. Raja Gopal, looking at this method, it's easier to say than to do. You have a really high dimensional problem from the images coming in, and if you have images coming out as well, right, you have very high dimensional feature spaces too. So you have to have some way to kind of, extract a metric, get some more concrete information out of this, and this is looking at an approach of computing some local receptive field analysis, so doing some on the interior feature space, actually doing some convolution-like operation to reduce the dimensionality there, and look at some different types of metrics that are looking at the characteristics of that interior feature space and how it might relate to the distribution or clustering. So this is kind of ongoing work in that area. Okay, the last thing I want to talk about is federated learning, also known as distributed learning. And I'm very excited about this for several reasons. The idea of federated learning is you have multiple clients that are each performing learning, but without their data leaving their institution. And as you can imagine, in healthcare and medical imaging, where sharing data across sites is more challenging, this could be a great tool to kind of get around that and allow us to pool much larger data sets, but again, with being very respectful of sort of patient privacy or institutional kind of data concerns. And I think in academics, research and development, part of our strength is that it's a distributed process. Lots of research groups working around the world to advance the science. And if this is a way we can connect our groups together, I think it's very valuable. So here's an example led by Dr. Raja Gopal, applying this to the problem of prostate MRI classification. Just a simple test case here, but this is a relatively hard problem, and actually you can see from these images at the top that across our two universities, which happen to be, I can reveal, in San Francisco and Los Angeles, not physically far apart, we're part of the same kind of university system, our images are actually relatively different. You can see endorectocoil or no endorectocoil. You can see the variations in the appearance of the ADC maps from diffusion weighted imaging due to some acquisition and vendor specific processing. In this case, if we try to model trained on one data, the generalization was just awful, almost a coin flip, or basically a coin flip, and vice versa. But if we do this federated learning, you see these 10 to 15% jumps in generalization performance, applying the models across to the other institution. So just kind of scratching the surface on proof of concept of what this could do in medical imaging applications. And there's there may be need for innovation in this space. There are just a couple of the aggregation methods that are available. One, FedSGG, where you send the gradients from the individual sites back to a central server. Very bandwidth intensive, but maybe a little more granular updates, whereas FedAverage, you simply send the model weights. And again, the central server that you need in this case takes either these gradients or the model weights and typically does some averaging or weighted averaging, updating of the kind of central model, and then can send that back to the individual sites. So some interesting methodological improvements that came across. One example was for the problem of MRI contrast synthesis. From a learning perspective, addressing the fact, well, that, like I just showed, you have inherent heterogeneity in data between different sites. And this is going to be a challenge in all model development and even in federated learning, where it's actually quite hard to debug and diagnose these problems in the federated environment. But here they added this personalization block, allowing the individual sites to have some sort of personal weights in addition to the shared weights, so to improve performance when you have this heterogeneity of data across sites. All right, so thank you very much for listening. I think I hope I conveyed that I have a lot of enthusiasm about this area, and actually it's important to really work on reproducible and generalizable AI. It's got a bunch of open challenges, but a lot of ways we can try to attack and solve these problems. The physics-based methods, Bayesian methods, some prediction type methods, or federated learning are all great tools that we have and can build. We can do, always push to do more sharing of data and sharing of code. And I think how well we can address these challenges of reproducibility and generalizability is going to have a huge impact on how much actually AI can affect and be used for medical imaging and in fact for other healthcare applications. So just give my acknowledgements and thanks to a lot of great collaborators, trainees, partners, and thank you all very much for listening. And I look forward to hearing some of your questions. Thank you.